Hi, I'm Vivek, here to give you a small summary of our work. The key takeaway is that we promote the adoption of incremental learning approaches to real-world scenarios, and while doing so, we observe that looking at accuracy as a sole metric provides an incomplete picture, and looking at energy consumption and computational footprint is essential. This is one of our research gap, along with the need for realistic scenarios and also addressing miscellaneous industrial visual environments. For computational complexity, we look at the floating point operations as well as compare task-wise energy consumption against the task-wise energy consumption for a naive strategy, which is joint training with complete data. Similarly, we also extend incremental accuracy to area under the curve for comparing incremental learning and joint training approaches. We collect data on 100 industrial objects under 4 different visual environments, as you can see here, which have their own attributes. It's the Envar 100 dataset, which is available to everyone. These are the 100 objects in the dataset, and we also include metadata along with superclasses, lengths, weights, and descriptors. As you can see, some objects tend to be quite similar in nature, which tends to add more complexity during incremental training. This is a summary of our approach. The data is application specific. We test real world scenarios, and we also look at task-wise computational footprint with regards to time consumption, energy, and floating point operations. And we interpret the contextual performance and also look at old and new class performance. For example, as you can see in one of the experiments, looking at old and new class data provides a better picture of what method remains rigid and what method remains plastic. When we change the sequences, we observe that there are some sharp fluctuations and a variance in the results, which was not seen during constant increments. Here we can see some results on the different subcategories of the data set, and we observe that the challenging categories, the performance drops much readily, and we can see similar phenomena for old and new class performance here. Similarly, as we expect, the energy consumption rises as we increase the memory budget and leads to a significant overhead. In this experiment, we introduce all the data here at this midpoint again, and this is a 6-month study for a long training. And we observe that class incremental learning with joint training update provides some interesting insights with regards to accuracy and computational footprint. We briefly categorize the approaches as plastic and rigid. The plastic implementations tend to learn new data much easier, but they also predict and more confidently predict the newer data, and the features learned from old data when tested at newer tasks, they tend to overfit to newer data, whereas for rigid implementations, the features learned from new tasks tend to overfit to older data, and old objects are predicted with a higher confidence. For project implementability, we observe that the optimal configuration of incremental learning tasks, as well as the performance and computational footprint trade-off, largely depends on the data, the incremental learning method, and also the availability. In conclusion, putting incremental accuracy in comparison to the energy consumption and training time or computational complexity provides a more fair and comprehensive comparison between different approaches. And performance on standard benchmarks doesn't directly translate well to practical use cases. Also, lastly, an emphasis on green AI is essential for sustainable broad-scale adoption of incremental learning in real-world scenarios. Here are some more resources. Thank you.